All right. I'm Kevin.
And I'm Shannon.
We're going to tag team these mission concepts. I'm going to start with the Europa Lander mission concept, as that some of the technologies developed for that effort fed into OrbiLander. We're each going to go for about half an hour and then go into questions for 15 plus minutes. So with that, I'll get started. All right. Can everybody hear me okay? Audio, good, excellent. Just flag me if it's not coming through okay. So given the nature of the audience, I wanted to kind of zoom out for a big picture of what it means to have a mission in formulation and in implementation. That's still coming through okay back there, Alfonso? Great. This is a classic NASA chart that shows you the mission life cycle, both for robotic missions, human missions, et cetera. You can see up at top, we go from pre-phase A all the way to phase F, which is closeout. Phase E is where we scientists come into play. Pre-phase A and phase A is also where scientists have a very important role. When you get to phase B, C, and D, that's basically where the engineers beg and plead for you to get out of the room because they have important stuff to do. Everything that you're going to hear about today qualifies as sort of pre-phase A work. And the Europa Lander, we made it to MCR, Mission Concept Review, and we were preparing to go through key decision point A before we got mothballed. For reference, Dragonfly, as Shannon can detail, has gone into, is almost through KDBC. Yeah, so we're right about there. I haven't shifted the green line there. Clipper obviously just launched, and then Perseverance, we're in extended phase E. So that gives you kind of a sense of how these missions come to life and what they look like as you move through the various phases. Now, with regard to Ocean Worlds, in the early days of trying to figure out an Ocean Worlds exploration program, we worked really hard with headquarters and various stakeholders to try and take a page out of the Mars playbook. Mars has done so well because they've had this coupled mission and technology kind of hopscotch with science goals, starting with some of the earliest missions you see on top there, going all the way to 2020, where initially we were following the water, and now we're actually seeking signs of life and also preparing for sending humans. With Ocean Worlds exploration, we began this great voyage with Voyager, Galileo, and Cassini. Now we've got Clipper and JUICE up there, Dragonfly soon to follow. And part of what we were working on with Europa Lander is not just a lander for Europa, but a suite of technologies that would enable exploration of ice-covered ocean worlds that don't have atmospheres. Obviously, Titan's got the capability of using a parachute because of its thick atmosphere. But landing on icy, airless bodies is kind of a new paradigm in solar system exploration. And then, of course, moving on to melt probes and getting down to the hydrothermal vents with some sort of HUI type vehicle. This is something I borrowed from Chris. And if you ask me when we're going to do that, maybe 2100, it depends. These days, it's hard to predict anything. And speaking of which, back when I was an undergrad, finishing up undergrad, a press release came out based on the Galileo results. And the projection was that in 2009, we would have this melt probe. And turns out 2009 came and went, and there's no melt probe yet. But we do have Clipper launched, so we'll take the wins where we can. I'll start out with a kind of a vision for what the Europa Lander mission looked like, what it encompassed, and then I'll go into a lot of details about how the mission came about and what specific measurements we made. And I'll finish with a fair bit on the tech development. So the mission was solar powered, leveraging what we learned from Juno and the Europa Clipper mission. And the spacecraft itself, the lander, was delivered to Europa via a carrier stage. And the lander was encased in a biobarrier. This full lander was to go through a bakeout for planetary protection reasons. The back shell of the biobarrier is not shown in this animation. Right now, you're looking at the bottom of the lander. So those are kind of the foot pads and the base plate. We utilized a modified sky crane, the same system that we've used to land on Mars twice. But in this case, we actually have a bit of a lighter payload. The lander itself is about 550 kgs. Curiosity and Perseverance are closer to 1,000 kgs. In this case, so all of the backbone of this animation is hard CAD and modeling. So the thruster firings that you're seeing there are actual thruster firings as projected by the modeling done by engineers at JPL. The thrusters were canted a bit more than they are for the Mars landing. That's to aid us in protecting the surface. Once on the surface, the high gain antenna comes up, makes contact with the Earth, direct to Earth communications. And then cameras and spectrometers on the back of the high gain antenna collect a panoramic view of the surface and send that image back to Earth. I'm going to skip the sampling part because I'll get to that later. But if we just take a look at how this mission, how the measurements for this mission and the goals came about, Shannon will go into a bit on flagship missions, New Frontiers missions, and Discovery missions. The lander concept was a flagship. And I think it's really important to emphasize, I've got a bit of a mission mantra, and that is that flagship missions should be your mission choice of last resort. If you can get your science done on anything other than a flagship mission, do it, because flagship missions just have committee after committee, review after review. Not that Discovery missions and New Frontiers don't, but those mission architectures and the way those missions are run are much more encapsulated and less subject to a lot of kind of whims and ways of various factors. So we received a charter from headquarters that provided us with a pretty well-defined set of goals. And I worked with headquarters to help develop this charter and the bullet points that you see at right there. The team that we assembled was pretty incredible. A number of folks in this room were part of our science definition team. Allison Murray and Jim Garvin were co-leads with me to help spearhead this effort. And along with that, over the course of the roughly 8 years that the pre-project existed from 2016 onward, we had many partners across the US and beyond. And I'll get into a little bit on that. So a brief history is that we had that science definition team convened in 2016, and we delivered our report in February of 2017. Then we had our mission concept review of that MCR in 2017, and a Delta mission concept review in 2018. In 2019, there were 14 instrument teams selected for instrument development. And that was a tremendously useful and valuable effort. Many of you were co-Is, if not PIs, on a number of those efforts. And that really helped advance both our understanding of the complexity of the measurements and the mechanisms whereby those measurements could be made. And over the course of that time frame, we also had some funding to retire risks associated with the technologies, the cost, the schedule, and the science return. So what were the science goals and objectives? Shown here is a sort of a circular representation of the high-level goals, and within each goal, you see various objectives, and within each objective, so these are each objectives, within each objective were a number of investigations. Today, I'm only going to focus on the top one, the first goal, the life goal, and I'll walk through each of the objectives and some of the investigations. At right is the cover of the Science Definition Team report, and at bottom is the link to that report. And also we had a publication with 287 authors summarizing that report and the technology associated with the lander itself. And despite the extraordinary weight, I did travel with 2 hard copies of the report. So I'll pass these around later and you can take a look at them. Oh, yeah, I got this little meme after the report came out. I didn't know this baby meme, but it was a sign of success that we made the meme world. One of the things that we were asked to talk about is benchmark environments. How did we come up with our measurement requirements and our levels of limits of detection? So within the Science Definition Team, we formed a life detection working group, and we selected a few different benchmark environments for those measurements. I do want to emphasize that when it comes to thinking about our abiotic background, our benchmark ocean worlds environments to first order should really be considered as sources of biogenic and thermogenic organics and compounds. That's kind of got to be our default approach to any organics that we find on Earth, whether it's stuff in Archean rock cores or stuff in the deep polar oceans. We've got to implicate biology first and foremost. Any abiotic background is potentially dwarfed by that biogenic and thermogenic overprint. In other words, as we well appreciate, everything is everywhere in the ocean. And a sort of corollary of that is that, in other words, our home planet, with our home planet, the default assumption is basically the exact inverse of our assumption beyond Earth. Here, we have to assume what we're seeing is biogenic, whereas beyond Earth, we should assume that it's abiogenic. How are we doing on breakfast? So I'll just quickly go through. We had Lake Vostok, the accretion ice that is over Lake Vostok was determined to be one good benchmark. The salty subsurface lakes in Antarctica were determined to be another good benchmark. These icy brines providing a good refugia for organisms. And our third key benchmark were the deep polar oceans, looking at the productivity and the abundance of organics and amino acids. And all of those coupled together to give us this chart. And in the report, we've got a whole chapter on benchmark environments and how we arrived at these different numbers for amino acid abundances, et cetera. And Allison Murray did a wonderful job of herding all of us cats to really distill out this table. And Allison is an amazing oceanographer and polar microbiologist. And one of the things that we discovered in this process is that so few of the measurements that we often think about making beyond Earth are actually made here on Earth. For example, when it came to what is the abundance and distribution of amino acids in our polar oceans, for the most part, nobody actually makes those measurements because it's not really hypothesis-driven science in our own ocean. You know, we've got a number of oceanographers here, and you know, that question of what's the distribution of amino acids in the polar ocean is kind of not that useful for some of the basic oceanographic questions. Meanwhile, it's something that we would love to potentially discover on a far and distant ocean world. So there's this interesting gap in terms of the history of measurements that have been made versus measurements that moving forward we would love to be seen conducted in these areas. And that's a topic of discussion, I think. And I should mention that, where's Jennifer Stern? Jen, are you here? Jen just submitted a great Ocean Worlds analog paper to JGR that helps encapsulate a bunch of this work. I do also want to mention that when it comes to benchmarks, Tori led this really nice thought experiment about benchmarks in the kind of energy and power landscape of an environment. And I won't go into detail here, but this line marks sort of the steady state biomass productivity as a function of energy versus cell density. And an issue that arises for many of our ocean worlds is you may well have a lot of energy available for biological productivity, but then you also have this issue of dilution. These oceans are incredibly large, and if you distribute these cells throughout a large ocean, now you're dealing with relatively low numbers by comparison to, say, Vostok. Vostok is in that range of tens to 100 cells per milliliter. So that's another area where we should think about abiotic backgrounds and the extent to which energy and power are useful. Okay, in the interest of time, because we can come back to these, I'm going to just rapidly go through various goals, objectives, and investigations. Within our life goal, we had the objective of looking at organic indicators, the detection of organics, looking at chirality, and looking at isotopic indicators. And you can see here some of the specifics pulled from the science definition team report. Those numbers are again tethered back to some of those benchmarks with margin on top of them so as to be able to enable the precision and accuracy needed to determine some of that, those abundances and patterns. Just looking at chirality, here's one where the abiotic background we set in part by looking at what we see in meteorites. Danny Glavin, Steele, others have done some incredible work on looking at exactly this kind of question of chiral distributions within meteorites and what kind of enantiomeric excess really makes sense in the context of abiotic versus biotic. And you can get excesses in meteorites that are close to 20%. And so if you found an excess on, say, Europa in the chiral abundance of amino acids, and it was at 15%, well, that is perhaps just an indicator of what we see in meteorites. So in order to actually get a biosignature, we argued that you need to exceed that enantiomeric excess of 20%, and then you need to measure it with an accuracy of better than 5%. When it comes to moving to the next objective, morphologic indicators, looking at different shapes. Within that, we've got investigations looking at micro and macro scale and also cellular properties. And there, the benchmark was again set by these polar environments. This is a really nice paper published by one of Allison's students looking at the population distribution of different size particles in Lake Vita samples, where at the 0.2 micron particle diameter, that is primarily Lake Vita microbes, whereas anything smaller was determined to be inorganic particles. And so that's what set that 0.2 micron limit. We looked at various instrument capabilities, and I'll get into that in a little more detail soon, but here you can see some of those candidate microbes along the left there that were used to help constrain and determine that measurement requirement. Another objective that we had within Goal 1 was looking at inorganic indicators, looking at biominerals, making sure we had the context of the inorganic composition to go along with any organics and morphologic indicators. And there we focus primarily on various silica, silicates, iron, sulfides. And here we can get into some of the chemistry of the ocean itself and what might be in solution in the ocean and how, say, different oxidation states of iron could be indicative of stuff mediated by microbes versus, say, kind of an Archean Canfield type ocean on Europa. And then context or provenance was the last critical objective within our Goal 1. So all of this, this is meant to be an eye chart, but there's a big fold out in here that's got every goal, objective, investigation, measurement, and candidate instrument in there. So I encourage you to look at that in great detail. The 5 instruments that the team determined were most applicable for our various measurement requirements were some kind of organic compositional analyzer. We use that as a generic term for something more specific like a GCMS. And then the sort of proven flight instrument column is shown here. With a flagship mission science definition team report, you are required to keep things at kind of a high, broad level, because ultimately what happens is that science definition team report gets used as a reference document for an announcement of opportunity to which the scientific community can respond and propose their own instrument. And so you want to kind of show viability of that kind of measurement, but you don't want to be overly prescriptive, because you don't want to rule out the possibility that, say, microfluidics and capillary electrophoresis, new types of technologies can come to bear on these things. But with those, with that model payload, all of the instruments could work in service to not just that goal 1, but also the habitability goal and the surface properties and dynamics goal. And the SOC asked us to also comment on our kind of philosophy for how we selected the various measurements that folded into the biosignature framework. This framework we heavily leveraged from the Mars community and the Mars 2020 Science Definition Team report. And there have been many NRC reports. So we had a tremendous amount to work from. But largely, our model payload philosophy was that not only do we need to have multiple lines of measurement, multiple lines of evidence, but we needed investigations that were highly complementary, so that if we had ambiguity on one, we could look at another. And then, heaven forbid, one is not just ambiguous, but one fails. We need some redundancy. And then a critical thing, given that Mother Nature doesn't care whether or not we actually find life on Europa or whether there is life on Europa, we need to make sure that our science return is intrinsically valuable, independent of whether or not there is life on any of these ocean worlds. And as I mentioned, there's a lot of work that has been done over the past 20, 25, 30 years on this. We also made sure, at this point in time, Mary was spearheading the development of the ladder of life. And so I had some conversations with her over the course of this process to try and make sure that our payload checked the boxes on the various ladder of life considerations. A very useful funding source ended up being the instrument concepts for Europa Exploration 2. This was the second instantiations of that. The first was for Europa Clipper. But with IC2, 14 instrument development efforts were funded. You can see the PIs and the various instruments shown here. And you'll see that not all of these fall into the types of instruments that we on the science definition team identified. And that's great, because we want to have that kind of investment to show capabilities beyond what we had conceived of. And within the science definition team report, we go into a lot of detail about some of the ambiguity with different types of instruments, and I won't go into detail on that here. With regard to life detection, it's one thing to discover a biosignature. It's another thing to have several different types of biosignatures. But to actually claim that you have found life, our team went through a lot of kind of soul searching of what that would entail. And working with folks at headquarters, we were kind of put to this task of what's called the podium test. When would somebody at headquarters feel comfortable getting up and saying, we found life? And so in that context, we mandated that for life detection, not only do you need to have multiple lines of evidence, you also need to have redundancy in the fidelity of that measurement. And so along those lines, our team came up with this biosignature bingo concept, where with each sample collected, we would give some sort of grade to the abundance of organics, some sort of pattern of non-Gaussian distribution, chirality, so on and so forth. And then the cumulative result would give us a green light on whether or not we are confident in that biosignature. To actually claim life detection, you needed to repeat that at least 3 times. Once you did that 3 times, then you could potentially get up to the podium and say that we have found life beyond Earth. Now, coupled with that, we also had a sampling sequence, and I don't have time to go into this in detail, but we imagined scenarios where you sample at, say, site A in the workspace, and for 2 of the sampling efforts, you check the box on biosignature bingo in the final column, but then the 3rd one, you get a negative. And so now you have to go to a different area. And a lot of this was motivated by the fact that with Europa Lander or Enceladus Orbilander or any of these missions that are far beyond the asteroid belt, you're going to want to employ a decent amount of autonomy and couple that with punctuated ground in the loop to determine where exactly to sample. Okay, confounding factors, I'll just note, I think everyone here appreciates that on Europa, we've got a very intense radiation environment. For engineers, that's problematic. For teasing apart the exogenous and modification fingerprint over the endogenous, that's also quite challenging. But from a planetary protection standpoint, I actually think the radiation environment serves us well because it sterilizes any spacecraft that lands. This plot is kind of a chart that lets you determine for a given surface age on Europa, how deep you would need to sample in a given region in order to get a sample that has not been significantly processed by that radiation environment. And interestingly, a lot of where CLIPPER is doing its closest approaches is in regions, these boxes, where you don't actually need to go to that great of a sampling depth. And so by the end of the mission, we had as a threshold a minimum of 3 samples collected and analyzed with science ground in the loop, so folks on the ground having a chance to say thumbs up or thumbs down on biosignatures, and many more samples possible with autonomy. Our mission lifetime by the end of our study was close to 90 days. That's comparable to the MER missions. And our sampling depth requirement was 10 centimeters, but the full reach of the robotic arm, as you can see here, it could potentially get as deep as about ½ meter. Okay, I'm going to finish with a bit on the mission and various trades and some of the progress that we made. Just to highlight a few key challenges when we think about differences with ocean worlds versus Moon and Mars. Communications, the delta V that we've got to get rid of, or that we've got to gain and then get rid of. EDL becomes DDL. There's no entry, there's no atmosphere. Power becomes really tricky. Solar, yeah, for the carrier stage, but not on the surface. So we had primary batteries. RTGs can solve some problems, but then they create other problems with planetary protection and mass, et cetera. And then sampling, there's of course a lot of new threads there. And a lot of this is addressed in that paper at the bottom. We went through a host of different trade studies from the power systems, telecom system, delivery and relay, and surface sampling. And we really explored this trade space very, very thoroughly over the course of that time frame from not just 2016. I started working on Europa missions in the early 2000s and Europa Lander concepts as far back as 2006. And here's where the rubber kind of meets the road. For all of the capability that I described with the instruments, when you roll into our threshold and baseline, the design principles mandate that you add margin on top of your best estimate for the masses. And so with that margin, you rapidly get up to, in our case, a payload mass of 42.5 kilograms. That's our maximum expected value. 42.5 kgs of instruments on the surface of Europa. When you roll it back, and this was a very high fidelity mission engineering study, when you roll that back to the launch pad, you're dealing with 15.5 metric tons on launch pad. A lot of that is obviously wet mass, but as you can see, the lander is in that range of about 575 kgs. That requires a descent stage of about 1,200 kgs and so on and so forth. So it's very challenging. The tyranny of the rocket equation just dominates, but that's the nature of the beast. We just have to deal with that. Quickly, our engineering team looked at all sorts of different tools. Early on, folks said there's no way that you can sample this ice at 100 Kelvin. It's going to be harder than concrete. The funny thing is that then I went to engineers at JPL and they're like, wait, concrete is actually kind of easy to sample. We've done all this for Mars. We've dealt with really hard basalts. Here's an example of our sampling chamber. This is about 4.5 feet high. You can see a pneumatic system here. This actually has some heritage with Dragonfly also. Honeybee was working with us and Dragonfly at the time. Our colleagues at Goddard did an incredible job of developing this sample handling system called CADMES. The high gain antenna shown at left there, the gold square, that was developed and thermvac tested. The various feet and legs of the lander were tested in great detail. Here's our gravity offload test bed. That's Stephen Reinhardt, as you can tell from the cap, and Lori Glaze coming to see. This is testing the leg dynamics under about 1/7 G or simulated 1/7 G. We also did a bunch of landing tests with a sky crane type of system up in one of the buildings at JPL. So here's the lander with its kind of marionette legs. These legs and the belly pan there, the circular disc, are meant to allow the lander to accommodate ice spikes and bumps and various things. And so on its way down, the sky crane lowers the lander at about 0.5 meters per second, and that's what you'll see here. And then John Gallen and team put all sorts of pathological constructions underneath the lander to test how these legs work in concert to then have the belly pan land the chassis of the lander on the surface at roughly horizontal. Then I'll just finish with a bit of our final tech dev effort where we took a full-scale lander out onto a glacier in Alaska. And this, whenever I watch this, it makes me feel like I'm on Europa because it certainly looks to some extent like Europa. But as we pan up, you'll see, sorry for the stuttering here, but you'll see our field team. And there's the lander off on the glacier. We helicoptered the lander in, and as a scientist, it's always just humbling to see how brilliant the engineers are. Within a couple of hours of having the lander on the surface of the glacier, they were pressing buttons and having it sample right away. And what we were testing out here was what I like to call push button autonomy. So the cameras on the mast here were scanning and taking images of the surface and then determining the best places for the robotic arm with its tool on the end to then drill in and collect a sample. And you'll see that arm in motion as we pan around here. And that particular tool has got this drill on the outside and it's hollow on the inside. So the sample is actually kind of within the fist of that drill there. And it then arcs up and deposits that sample in what for the field was just a bucket. But this was a beautiful demonstration of autonomy and autonomous sampling in a real world environment on this glacier up in Alaska. So I'll finish there and we'll hold off on questions and we'll go directly to Shannon. Thank you very much. Tuesday. There we go. I think that should all still work. Sorry.
All right, I'm gonna follow up. Kevin very kindly, even though I was listed first on the schedule today, I said, Kevin, will you please go first? And he very graciously accepted. And I think that that is really important because this study, the Enceladus Orbulander concept, was only possible because of all of the excellent work that the Europa Lander science definition team did. I have my own copy of a hard copy of the team report that lived on my desk for, the 2 years that we did this, sort of year and a half that we did this study. And I can't tell you how many, it's very well worn at this point, because I was just constantly referring to the studies that the team did, like Allison Student that you were mentioning, the rationales that were detailed in that report. I just cannot stress enough how important having that kind of thorough documentation and thought process available to the community facilitated this study. So Enceladus Orbulander, as you hopefully took away from Frank's excellent overview yesterday, was created to address this fundamental question of, is Enceladus inhabited? We went in with our primary goal being life detection. Most of the missions that have actually happened do not have life detection as a goal. And we wanted this to be the primary goal of the return to Enceladus, because it's well motivated by the Cassini data, as Frank told us yesterday. I know that Kevin already spoke about this and Morgan spoke about this, but it's worth repeating, especially if you're not in the churn of this cycle, because it's kind of hard to wrap your brain around. So on the left-hand side, we have the smallest possible missions, that's Discovery. And then you have that medium class mission that Morgan talked about, New Frontiers. Dragonfly is the latest example of that. And then on the far right-hand side, we have the flagships, and those these opportunities are supposed to kind of scale with inversely, right? So the big flagships do not come around as much. They're need a lot of community buy-in, so they're driven by the decadal survey. The New Frontiers are supposed to be cost a little bit less, and then come around a little bit more frequently. And then the Discovery program is supposed to be pretty small and efficient in getting things done. I've put numbers on this slide because these are the numbers that are traditionally thrown around. But one of the challenges to mission implementation is that these numbers are not real. There's a number that gets put in like the AO for Discovery or New Frontiers, and what that number actually accounts for is like a moving target. The PI managed cost kind of depends on what's available with the launch vehicle, and then there's all these other costs that like NASA has responsibility for. I do not fully understand that whatsoever, but I think it's important as a community to remember that even though we talk about these three different classes as these three bins financially, that's not how it actually works out. It's kind of just a story we tell ourselves. But the important thing is that the science, we do all, while the numbers may change, we do kind of have a good community conception of what is the science return expected from these different classes. Because obviously if you're working with a smaller pot of funds to work with, you have to really be focused on your science goals. And I like what you said, Kevin, about scoping. Well, I'm going to rephrase what your mantra of flagship science for flagship. We really have to scope our science expectations to the resource boxes that we have. And so we went in with the expectation that the sandbox that we were playing in was a flagship. but just because there's a greater than 1 billion sign doesn't mean that you can go absolutely crazy, right? We wanted a sandbox that someone would, like Congress, would buy. So we tried to keep our appetite aggressive, but not crazy. I shouldn't use the word appetite right this morning. All right, so just to put in perspective, the work that Kevin and his team did was part of this pre-phase A, a long dedicated study. Our Enceladus Orbilander is a mission concept study that was conducted to feed into the decadal survey at the request of NASA for the National Academies. So in 2019 is when the proposals went into this new process of NASA asking the science community, what mission concepts do you want to study for the decadal survey? And so we put in this, hey, let's go to Enceladus and look for life, and let's do it on a flagship. What would that look like? So this started in October of 2019. Then we had 2020 to work on it. So that was really fun. We actually got our science team and our first mission concept study run in person before, what happened. And then by November of 2020 is when we, August of 2020 is when we delivered our report. So you can see that this was a much more accelerated timeline. And that's why I credit Kevin and the community for putting out all of these fantastic resources that made this study possible. Then by March of 2022 is when the National Academies report that made that final recommendation, that's when that came out. So this is a very quick timeline. All right, so the SOC asked us to a couple questions to guide our discussions here. So this next part, I'm going to hopefully get you thinking about why different measurements were included as part of our Search for Life objective and what the rationale behind the measurements as a suite were. So as I said, our #1 goal for the Orbilander, it wasn't an Orbilander yet, but we had a in-person team meeting. It was 2 days, very concentrated. There are some folks here who are in the room, Morgan, Alfonso, Jen. So feel free to pipe up when I misspeak. And one of the things that we sat down and we said, okay, we know that the Search for Life is well motivated by Cassini data. What in the Cassini data is just like a surefire measurement? We're going to get there, we're going to measure something, and that something is going to tell us, give us not just a yes, no answer, but like an understanding of what's in the plume. So we first targeted chemical biosignatures because they're well supported by Cassini data. So the amino acid characterizations that the Europa lander also targeted, thinking about abundance, distribution, and chirality. We really wanted to get at isotopes, but couldn't figure out a way to do that with the currently available payloads. Same thing with lipid characterization. And then we also wanted to get after that pathway complexity index. So thinking about what subunits do we see in the mass spectra and how, what's the minimum set of those subunits that you could use to make a big macromolecule. We thought that was a really compelling chemical biosignature that we could go after. However, these are well-supported data, well-supported measurements that we could make, but for the podium test, it would certainly be hard for me to go home to my mom and explain like, yeah, Mom, we found life on Enceladus because the amino acids don't look the same as what we expect here on the Earth. She'd be like, that's nice, sweetie. That's harder to write a headline about. And so we thought about what are some more higher risk, so more difficult measurements to make, perhaps less well motivated by the data that we have, but higher reward. And we loosely termed these as the confirmation biosignatures, something that you could stand up on the podium and wave the "We Found Life" flag. So the two that we went after were identifying a genetic biopolymer. So looking for something that either was DNA, which that would be pretty sweet, or could serve as the function of DNA, so having that repeating charge backbone. And then we also put in there cell characterization using some of the microscopy methods that Kevin showed, some subset of that to characterize potential cells in the plume. And so together we thought that this built a compelling scientific investigation where you kind of lay the framework for what we understand about the plume, what could be there, these chemical biosignatures, and then kind of build a pyramid of confidence looking for these other harder to get at, but perhaps more convincing biosignatures. Together that created this payload, and I've ordered the different instruments as like higher TRL or higher readiness level on the left-hand side going over to the right-hand side. Like with the Europa lander, we were trying to keep things more generic. Enceladus Orbilander should not be flown actually as we described, because things have happened since 2019, 2020, and we're getting better at different instrumentation. So this is just an example payload that one could fly. The nanopore, for example, was kind of our we allowed ourselves one like miracle payload element. We don't have a nanopore that's like ready to go off the shelf to do the kind of genetic or the biopolymer search that we would like to do. But we think that we're close. We think that we could get there in a timeline, a realistic timeline for executing this kind of mission. So one of our messagings coming out of this study was there is more instrumentation development work that needs to happen, and NASA should support it. You may recognize this ladder of life detection from Kevin's slides. We also were thinking along those lines of building a payload that would be robust to different rungs on the ladder. If you haven't checked out Mark Naveau's paper about this, it's full of awesome graphics. If you know Mark, he's just really good at making those. I heard a lot of nods, yeah. And so we wanted to get multiple rungs along the ladder, and then especially for key measurements, wanted to have multiple ways of making those measurements. So, heaven forbid you lose a capability with one instrument set, you can still make that same kind of measurement with another instrument. So that was our complementary and orthogonal approaches. All right, so when we were building our science, our STM, our science traceability matrix, we were really concerned about context. Not perhaps specifically about the abiotic background, but trying to put these exquisite chemical measurements that we planned on making in the context of the Enceladus environment. We thought that this was the key discriminator between perhaps doing Enceladus science on a New Frontiers budget versus doing something at a flagship. That what the flagship allowed you to do was get different levels of context that are not available at that medium box. So we really focused on that context as a key goal. So at Enceladus, what does that look like? Well, one of the key things we don't understand is the specifics of those ejection mechanics that Frank walked us through, like the best of our understanding, inferred from the Cassini data. What is actually happening between the ocean and the ice? We wanted to provide measurements that would help better tell that story. We also wanted to be able to place those chemistry measurements of potential biosignatures in the context of what's happening in the ocean. What is that ocean environment? Is it very dilute? Are there concentrated areas? This is a difficult story to tell at Enceladus, where you're just flying through the plume, and that plume material may have been modified on its journey upward. And so there were a lot of different questions that we were trying to answer in that goal. So this put our context suite into two categories. We had our remote sensing and our in situ. When we started this process, we were looking at orbiters, we were looking at landers, and then the Orbilander concept kind of came out naturally. So originally we had two very separate buckets, and then it turned into all one thing. So context instruments including cameras and spectrometers to help us identify a safe landing site, Frank put it well yesterday that we don't have the data necessary with Cassini to actually pick a spot on Enceladus and say, yes, that one, that's the place we want to put this very expensive laboratory. Instead, what we know from Cassini data is that their places should exist, and that we would be able to identify them with a payload suite like this at the surface of Enceladus. So here's just another way to summarize our payload. You'll see that some of the life detection suite instruments also serve in this context investigation over on the right. So what is this actual mission concept that we came up with? So the Orbi lander concept came to be because we were looking at orbiters, we were looking at landers. What if you had a like a deployable lander, kind of like what Frank was talking about with the ESA investigation. And then we took a step back and realized that most of the delta V, the slowing down that you have to do to get to the Enceladus system. Saturn is the second largest planet in the solar system. It's pretty big. Enceladus, as we learned yesterday, is so tiny. It's only 500 kilometers in diameter. So Saturn is pulling a lot on you when you are in orbit. And in fact, it is, you don't just get into orbit around Enceladus and stay there and, continue the rest of your mission. We are constantly having to fight against that gravity and do orbit maneuvers to maintain that orbit. And so we thought, okay, what if we let go at some point and just do a controlled landing? It's more complicated than that. But if we take the whole spacecraft down to the surface, it's a lot easier than perhaps coming in straight away or maintaining an orbit for 4 years. Yeah, I still can't believe that Alfonso, I think you were in the room when we were all like, yeah, let's just bring the whole thing down. That'll work. It's not as crazy as it sounds because Enceladus is so tiny. You've already shed all of your delta V from coming in from the inner solar system, just getting into orbit. All right, so what are we doing in orbit? We notionally said a year and a half. We'd be doing the full set of life detection suite measurements except for the nanopore because you cannot get enough sample just with our 1 meter cone of acceptance, of a cone of receiving material as we fly through the plume. So that is the only measurement that we don't make in orbit and on the surface. We would only do it on the surface. We'd also be sampling the plume vapor. We'd be doing the context measurements, trying to understand the geology of Enceladus, but also trying to find a landing site as the primary goal. And we estimated based on the size of our pixels on the surface and where we would be imaging in these different orbits, that it would take us a year and a half with margin to identify a suitable safe landing site. Plenty of time, we thought, for the scientists to argue for many weeks about where to exactly put this thing down. So the orbits are this petal orbit, and it kind of rotates in and out of the plane that we're looking at so that we would be actually sampling different parts of the plume. You saw in some of the graphics that we saw yesterday that the tiger stripes are, there's 4 of them and they actually differ in their activity level. So getting kind of a suite of fly-throughs we were really excited about. You see that we spend much of our time not doing a fly-through and instead sending data back or recharging our batteries. But then once you get to below 100 kilometers, we're doing our primary science at that periapsis. All right, so after we've found our landing site, we're really confident in that we've done sufficient analyses on the plume material that you can capture in orbit. We then transition to this landed phase. We estimated that at about 2 years, and the wiggle there is because there is wiggle room. If it takes you longer to find a suitable landing site, that's okay. It comes at the cost of the landed phase. That's a decision that the science and engineering teams have to make. We would do the life detection suite again, this time with two different acquisition modes that I'll get to in a minute, the passive and the active, and then also do seismic monitoring and imaging of the samples that we acquire. All right, so why this bifurcated approach? Well, the plume is such a gift. Up at the in the plume, 20 to 60 kilometers, you've got vapor, you've got micron to nanometer sized ice grains. These are the materials that Cassini sampled. We want to go back and figure out what that high molecular organic content that Frank teased yesterday, what is that? We can do that flying through. Because we're in orbit, we do it very slowly. So you can take advantage of that intact grains. But then once you're on the surface, you have access to much larger grains. These grains do not have sufficient energy to reach those 20 to 60 kilometer altitudes. They fall back to the surface beforehand. And we think that those larger grains should have a higher signal of that organic material. So we were really excited about using that same funnel that we would fly through the plume and just point it up at the sky like it's a snowfall and you're a kid and you have your tongue stuck out to collect grains as they fall onto the surface. But because we're already on the surface, we want to also access what has previously accumulated there. So we have our fly through, which is a passive collection as we're in orbit. We have catching once we're sitting on the surface and we're just letting material fall into the funnel. But then also we want some control. And that would be some kind of active mechanism. For the purposes of this study, we used a scoop, but maybe it's a rasp, maybe it's a really fancy vacuum. Who's to say? Someone probably, in the next 20 years or something. And by putting all of these three together, we figured that we would get like a profile of the plume and the different particles that are being ejected in it, and different volume amounts, allowing us to do things like the nanopore analysis, which requires so much more sample than we could acquire from fly-throughs. So putting all of this together, we felt confident saying that a mission like Enceladus Orbulander could detect life if it was at this assumption that we made that life in the Enceladus ocean would be 500,000 times scarcer than in Earth's oceans. Again, this is the context suite that we put together, and this was our original timeline that we worked to. You'll see that science operations in the 2050s, but that's starting very soon with a launch kind of at the end of the 2030s, which would require starting tomorrow. So we'll see how things actually unfold for Enceladus. The good thing, as Frank said yesterday, is that as we exercise patience, the south pole of Enceladus will become more and more available. Will start to be in southern summer rather than at this point we were just coming out of southern winter when Orbulander would arrive at Enceladus, which means not all of the pole would actually be illuminated, which limits your landing site selection, but not in such a way that would preclude the science that we were trying to do. All right, so very quickly, I'm going to finish with this, again, amazing Marc Neveau graphic that I think summarizes best some of the concerns that we had about that possible abiotic background. And for us, it really came into the question of sample sufficiency. So if we have this current state of knowledge of what the Enceladus energy supply might be and cell energy demand, you'll see that there's a lot of uncertainty on those values because we don't know what the Enceladus ocean is like. So we picked a value for our design, that's that 10 to the third cells per mil in the ocean water, because to make a mission like this happen, you have to start with an assumption. This is, we thought, perhaps not the most conservative value. but it also wasn't the most optimistic, which I think is a healthy place to be. We also know from the payload instruments that we were working with how much material they would need, how much signal they would need to make the measurements that we were asking them to do. That's their limit of detection. So each payload has a different requirement. Like the nanopore sequencer needed so much sample. But you could imagine that there's a limit of how much sample you can actually acquire and run through your instrument suite in the actual lifetime of a mission. Putting those together are, we had, again, as part of the study, we were thinking about orbiters, we were thinking about landers. We loved the Orbi-Lander approach because it got us at both of these ends of the spectrum, if you will. So in orbit, we were able to do many pass-throughs of the plume, access the smaller grains that Cassini did, smaller grains, and do a characterization of the plume up there. But in order to build up enough sample to run some of these more sample-heavy instrumentation, we needed to get down to the surface to do that active or passive collection. 3 minutes. Yes. Oh, yeah, for sure. Took me about 3 minutes to comprehend that. Sorry. Had a lot of coffee on an empty stomach. Okay. So just for context, some of the New Frontiers ideas for going to Enceladus are kind of over there. Europa-Lander is going to a different body, so they made different assumptions about the cell density. What having these different levels of sample got us, we thought, was kind of buy-in on how much resiliency against the possibility of, okay, we scooped something and we saw nothing. Is that because we didn't scoop enough, or is that because we scooped in the wrong place? Like all of that uncertainty. The context measurements, like our geochemistry, can also kind of collapse that uncertainty of, okay, we didn't see anything, but also it's really, really salty. So maybe we didn't expect to see any biosignatures in here because of that high salt content. And so by putting all of these things together, we thought that made the mission astrobiology result much more informative than yes, no, but rather there's no signs of biosignatures here because the environment is scarcely habitable. Or, wow, the environment is really habitable and we still didn't see any biosignatures. That must mean that the life didn't arise. It's about to arise. Who knows? There's more context was a really key finding of what we were able to bring to the table with a flagship mission concept. So in summary, the Enceladus Orbi-Lander was a mission concept study. It's not a thing. It lives on paper. I get asked that all the time, like, oh, where's Orbi-Lander at? It is a report that you can read. It was recommended by the Decadal Survey as something to pursue, but as Morgan well stated, there are other things in the queue, and who knows when this will actually happen. However, I think that what our study demonstrated is that we are ready to go. We're ready to go to some of these worlds, these ocean worlds, make these life detection measurements, and see if there is life there. And whether it's the Europa-Lander, Orbi-Lander, I'm not sure. I hope it happens in our lifetime. That's a very dismal way to end this, but I think that we can do it.